All right. So, we're going to pick up where we left off yesterday. We are maximizing, okay, our surface area to go with our volume. Remember, maximization. You have to get one. You have to read the problem. What are we trying to maximize? Figure out what that is, or minimize, as the case may be. We need to find an equation that works. We need to make sure that equation is in one variable. You can't do it with two variables. We will deal with more than multivariable or multivariable stuff later on. We're not going to truly get into multivariable calculus. That's like Calc 3, but we're going to touch on some stuff a little bit coming up at the end of this chapter. And then we want to then you take the derivative and you find the max or min. Okay? And you have to think about endpoints and stuff along those lines. Now, here's the deal. I have a particular volume, okay, 1 liter. I want to make a can that holds 1 liter, and I want to minimize the surface area. So this is not an unusual thing. Okay, when you're designing objects and you're designing containers for something, and this happens more commercially than it does for retail. Retail is a whole different story. There's more to than just size, but you don't want to spend a lot of money on your container that you don't need. If you can save a penny on every can of soda that Pepsi sells, even if they save a half a penny, that's a lot of money in the end, right? It adds up in a hurry. Doesn't take much to make a major change. So this is the kind of thing where you're trying to find what will work in certain situations. Now, I always like to think of cereal boxes. Okay, they are not the most efficient use of surface area to volume, but they have a secondary purpose: display. Okay, they're the shape they are. Part of the reason they're the shape they are with a big flat surface area is display, catch people's eyes. They are not the best volume. The best surface area to volume are cylindrical, or spheres would be better. Okay, if you can do spheres, but it's awfully hard to put a bunch of spheres on a shelf. Okay, so that's why cans work really good. Okay, and particularly for liquids, cans work better than they do for solids. But there's a reason they are the shapes they are, is in order to get that display surface area. And you've got that flat surface area with the display, it stands out. Okay, so there's other reasons to look at it, but this is one of them. Commercially speaking, if you're doing something that's not being sold for retail, this is a big deal. Okay, finding a container that fits. So I want to do volume. So I have a couple of equations here. This is my volume equation. Okay. So the volume of the cylinder, pi r squared h, equals 1,000, because 1 liter is 1,000 centimeters cubed, or 1,000 cc's, right? Cubic centimeters, okay? Or 1,000 milliliters, cubic centimeters and milliliter. And you should know your metrics. But what we're trying to minimize, we're not trying to minimize the volume. The volume is a fixed quantity. That's a fixed equation. What we're trying to minimize is the surface area. And if you look over here, the can is broken up into the two parts. You got the top and the bottom, and you got the side of a can. Because you take a can and you cut it and you unroll it, what do you get? You get a flat square. Okay, so we're trying to do the surface area. By minimizing the surface area, we are actually minimizing the material used to make a can. Because you can figure pretty much it's a uniform thickness. Sometimes it's not, but usually it's a uniform thickness. So if you minimize the surface area, the thickness doesn't really matter. You're still minimizing the amount of material used to make that can. That's what we're trying to do. Problem is we have two variables in our surface area problem. We need to eliminate one of them. Now, we can eliminate R or we can eliminate H. Much easier to eliminate H than it is R. Because I have R in two parts, but I only have H in one part of the equation. So what you do is you go up to here, this top one here, your volume one, and you solve that for H. Divide both sides by pi r squared, and you get h equals 1,000 over pi r squared. That's the relationship between the height and the radius. Okay. Take that, plug it into the area formula. I'm going to go ahead and extend the page because I know I'm going to need the space to work. Area equals 2 pi r squared plus 2 pi r times 1,000 over pi r squared. All I do is substitute what h is. Substitute it in. Area equals 2 pi r squared plus, this reduces down, your pi's cancel, one of your r's cancel, so you get 2,000 over r. Okay, so all I've done is take the area, make it into one variable. Now you begin your calculus. It's only one step in this whole problem that's technically calculus, right? Taking the derivative. When in doubt, take the derivative, set it equal to 0. A prime equals 4 pi r minus 2,000 over r squared. And what do we do to that? We set it equal to 0. So I can solve, do some math, do some working out. So if I get 4 pi r equal to 2,000 over r squared, right? Divide both sides by 4 pi and multiply both sides by r squared. I get r cubed is equal to 2,000 divided by 4 is 500, right? So I get 500 over pi. R equals the cube root of 500 over pi. Now, that is really a wonderful, beautiful number. I love that number. No, I love that number because it's an exact value. The problem is, we are mathematicians. We like exact values. Whoever's building this thing, though, is some silly engineer. That ain't going to work for design, is it? You're going to go tell the guy, okay, here, I figured out what the radius is. It's the cube root of 500 over pi. They're going to look at you like, really? That helps me so much when I'm purchasing my materials. Okay. So what do you need to do? You need to convert that over to a decimal. You bust out your calculator and you give them a decimal approximation because that's what engineers do. It's like, what's the definition of pi? You ask a mathematician, it's the circumference of a circle divided by its diameter. Ask a physicist, it's 3.1415926, give or take. Ask an engineer, that's about 3. So R equals what?
5.419.
3 decimal places is good enough for me. And do 3 decimal places truncated around it. Get in the habit of doing that whenever you're doing decimals because you want to prep for the AP exam. You want to prep for the AP exam. So we found the radius, but I'm sure we did not actually finally answer. What's the question? What dimensions use the least material? Okay, we know what R is. Plug R into here to find the height. Then you got your radius and your height. You know what you need. Okay, it's easy enough to finish off the problem. plug the radius number you got into this one. Do not plug it into here and then solve. You've already got it solved for h. Plug it into that one. And then you got your height and you got your radius. Okay? Questions? This is not an uncommon one. You have problems like this in your homework. I really enjoy this kind of thing. I see the practicality, designing vats, designing containers, finding ones where you have a fixed volume that you need to fill, but you want to, and you may have some restrictions on the shape, but not a full restriction on the shape. What's going to work? What's not going to work? This is important stuff along those lines. You know, I'm trying to meet it. If you have a hunk of material, what's the largest volume you can get and with the particular shape, particular amount of material you have? What's going to work for that? Okay? Does that make sense? So like I said, you can start to see where, oh, this makes sense. I can see how this works. Now, you could also test and do trial and error, but you're going to waste an awful lot of material doing trial and error. But if you do the calculus, you can figure it out right away. Okay. Okay, so I kind of want you guys to start this one on your own. So you have been asked to design a poster for an upcoming concert. It contains 60 square inches of printing with a 3-inch margin on the top and a 2-inch margin on both sides. What dimensions will minimize the amount of paper used? So here's what you need to do. Draw a picture. Draw a diagram. Oh, please, draw a diagram. That is what you absolutely have to do, is draw a diagram. Okay. We have a poster that has printed area within and margins along the sides. Okay. We don't know how big the printed area is. We don't know how big the whole thing is. It's easier to label the printed area on the inside. We call this X and Y. It makes it really easy to set up equations. So we know that it contains 60 square inches of printing. So that means X times Y equals 60. That gives me the printed area. But what am I trying to minimize? I'm trying to minimize the paper area. So I'm trying to minimize these dimensions. So this one going across here, X plus 4. This one going across here, Y plus 6. So the thing we're trying to minimize is we're trying to minimize the area of the paper, which would be X plus 4 times Y plus 6. So what do we need to do? We need to solve that area one, the one we're trying to minimize. We need to make it into one variable. So I take the other equation, X times Y equals 60. Let me go ahead and change colors on this one to kind of change colors. Erase and don't actually do it. So if I go back to this one here, for my given information, the printed area is 60 square inches, X times Y equals 60, solve one of those for X or for Y. Go ahead and solve for Y. Why? Because I feel like it. So Y equals 60 over X. Or you could do X equals 60 over Y. Either way, in the end, you'll end up with the same dimensions. Doesn't matter. Okay. Now I need to do substitution, and I have a choice of when I do my substitution. I can substitute now and then multiply, or I can multiply out and then substitute. Because I don't want to take the derivative with the parentheses. Please, it's just not worth it. It's easy enough to FOIL out that binomial, right? What I suggest doing is actually FOILing first and then substituting 60 over X for Y. I think it makes it a little easier. It's not that much harder, but it makes it a little easier. So my area equals xy plus 6x plus 4y plus 24. You see what I did? All I did is FOIL it out. I don't have any like terms to combine up yet, and I may not anyways. Put in 60 over x in for wherever y is. A equals x times 60 over x plus 6x plus 4 times 60 over x plus 24. Simplify. What happens here? These x's cancel. So I get 60 plus 24. So my area, 60 plus 24 is 84. Plus 6x plus 4 times 60 is 120 over x. $240, thank you. Thank you, thank you, thank you. It's the simple things I screw up. I'm just seeing if you're paying attention. No, you don't believe that? No, I never believe teachers when they ever say that either. So I now have a formula in one variable. And like I said, you could have substituted in the y at the beginning and then multiplied out. You'd end up with the same thing anyways. Okay, it's 6 to 1, half dozen to the other, whatever one you like, whatever floats your boat, so to speak. Okay, now what do? Take the derivative and set it equal to 0. A prime, you can't at this point. 6 minus, thank you, 240 over x squared. When you have x by itself in the denominator, just make the thing negative and make it x squared in the denominator. That's all you have to do. There's rules, but there's at some point you start picking up on some of these shortcuts, like the derivative of the square root of x is 1 over 2 root x. You just do it often enough, you start picking up on some of these shortcuts. This is one of the ones you ought to start picking up on the shortcuts. If not, I don't care. Take the derivative, however you need to do it. Rewrite it as x to the negative 1. Just get it done directly. Set this equal to 0. So I get 240 over x squared is equal to 6. So I get x squared is equal to 240 divided by 6 is what? 40? 40. So x equals the square root of 40, which is approximately what? Once again, we're sending this off to printers. Printers are even dumber than engineers. What? 6 point what? 324? 324 truncated, 325 rounded. Either one's good with me. So we found our x, our dimensions, however, it asks for our dimensions, right? So we know what x is. How do we find y? Take 60 divided by that. That gives us our y. And our dimensions are 6.324 plus 4, so 10.3. And then take 60 divided by that. It'll give you about 8 something, I think. Yeah, just guessing off the top of my head. 9 point something?
9.4887.
Ooh, 9.4876. Which, you know what? If we're giving this off, so we end up getting, what is it? We got y equals 9.4876. 7's truncated. So our dimensions are, we're going to have, let's see, 10.324 inches by 15.487 inches. You think that's going to go over well with the printing company? Probably not, but you can say this is what we want, and they can cut it down a little bit. Maybe make it a little smaller so you make it work. It's easier to go smaller than go over, but you get the idea. Okay. Once again, a practical use. Okay. For one poster, not that big a deal, but for printing millions, it's a big deal. Okay. So these are things you need to think about. When I worked at the fisheries, at one point, one of my jobs was we had to put nutrition labels on our cans of crab meat and shrimp meat. And I found out how they do the printing on the cans. It's 4-color printing. It's only 4 colors that they use to print the cans with. That's it. They print the white, they print the black, they print the yellow, and I think red was the other color we used, or blue. And then it was a combination. Shading, how much, and where they overlap. Gave you the different colors. But still, 4 colors wasn't. Why was it 4 colors? Cost. We could go with more, but it cost a whole lot more. 4-color printing was the standard. You know, going more than that really costs a lot of money. We didn't need more than 4 colors to get our logo and the name of the company on the can and all the information. Okay, these are things I had to figure out how big the nutrition label was that went on the can. Yes, that was a very interesting time for me. Okay, why don't you give example number 7 a try? See if you can figure out what you need to do. Okay, that's enough torture. Well, some people have gotten it, I hope. So, minimum at x equals 2 means that f prime of 2 has to be 0. Okay? Point of inflection at x equals -1, f double prime of -1 has to be equal to 0. So here's what you do. Take the derivatives, plug in 2 for x, plug in -1 for x, solve for a and b. So f prime of x is 3x squared plus 2ax plus b. Okay. So f prime of 2, plug in 2 for x squared for x. So you get x squared, that's 4 times 3, so you get 12. Plus, put in 2 there, that gives you 4a plus b needs to be equal to 0. Okay, I got 2 variables, I got 1 equation. I'm kind of stuck at the moment, but I've got it narrowed down. I know what the relationship between a and b is. Now I go over here, I do the same thing for the second derivative. F double prime of x, derivative of 3x squared, 6x, derivative of 2ax, 2a, derivative of b is 0. Ooh, 1 variable. That makes it nice. F double prime of -1 is -6 plus 2a, and that's equal to 0. Which means that a equals 3. Plug a in here and solve for b. So 3 times 4 is 12, so b equals -24. The key is understanding where are my minimums, where are my critical points. Oh, the first derivative is equal to 0, the second derivative is equal to 0. The first derivative at this point is equal to 0. The second derivative at this point is equal to 0.
How do you know that it's equal to 0?
Where are your maximums and minimums at? The only places they are located are critical points, where the derivative is equal to 0 or undefined. That's a polynomial. It will never be undefined. So the only places I'm going to find a maximum or a minimum are going to be at my critical points where the derivative is equal to 0. Only place I find the point of inflection is where the second derivative is equal to 0. And the polynomials, I guarantee if you get a 0 there for a polynomial, you're almost guaranteed to have a max or min. But those are the only possibilities. I don't have more than 1 possible value for A. I don't have more than 1 possible value for B. These are my only choices. They've got to be the answers. If I got more than 1 choice for them, for some reason there were squares involved with the A's and the B's, I might have to decide which one gives me an actual minimum, which ones actually give me the point of inflection. You're not going to be asked to do that much work. It's going to be like this, where you have 1 A and 1 B possibility, and that's it. Okay? But yeah, the key to this is understanding. Remember, points of inflection, critical points. Where do you get your critical points? Where the derivatives equal to 0 or undefined. Where do you find your points of inflection? Where the second derivatives equal to 0 or undefined. You have to remember that. You've got to remember, we may be moving past something, but we will never, ever, ever leave anything behind completely. Okay, when we get to the AP exam, everything we have covered this semester, except for Chapter 1, will be part of the AP exam plus the new material we learn next semester. You will have questions on limits on the AP test. Not a lot, a couple. Okay, you will have questions on how to take, you will have to take derivatives, you will have to do integrals, which comes up next semester. You will have to apply them, you will have to write tangent lines. Everything that we have done will be fair game in one form or another. And they do not ask, the multiple choice